All right, welcome back everyone. I'm calling this video, Let's Talk About GFC. So the 2D framework project that's designed to help facilitate the creation of a 2D game engine is called Game Framework 2D. Spoilers, I also have one called Game Framework 3D that is based on SDL and Vulkan, designed to facilitate the development of a Vulkan-based 3D game engine. But I got tired of maintaining the code base for a lot of the common stuff that was between them, so I forked off a section of it for all of the common or core functions that I found to be very useful to have in both the 2D and 3D game engines. So part of the process of installing GF2D and GF3D is the submodule GFC needs to be cloned as well. This is also written in C. I'm going to have a whole video in the future on the why of C. But for now, let's just go through what some of the features are that you have available to you in the GFC package. I mentioned during my discussion on resource managers that GFC has an example of a functioning resource manager, and that is the audio.h and its companion audio.c. This follows the same design pattern of we define what the resource looks like in the header file. Here we have a typedef struct, and we're defining something as a sound, and this is basically just a wrapper around the SDL mixer chunk, which is how they handle audio. So I guess this is also going to serve as my audio video. We keep track of the file path, so if we want to open up the same sound twice, we don't have to. We can see we already have one loaded, and we can increase our reference count rather than to have to. And then give a pointer back to this additionally. Now, we also have volume and default channel that gets set here with the mix chunk. When we load it, we set its volume. And something else that is useful is channels. I'm actually not going to go into that in detail now. I'm going to also save that as well as sound sequences for a later time. But if you want to work with the audio system, like with any resource manager, you have to initialize the manager. A note is that I take enable MP3 and enable OGG as flags in the initialization, because depending on your architecture and the licensing involved and how much money it costs you, you may not have access to MP3. If you're like a Linux GNU purist and you don't want to pay for the MP3 license, then you're going to have to use OGGs. And OGG doesn't always come standard on every operating system, so that is enabled as well. But with whatever you use, make sure on your system you're using music in the channel format that the file format that you are comfortable with, or that you have the ability to work with. I've had a lot of students in the past try to get the audio system working, and I can't get MP3s to work. I can't get MP3s to work. Well, do you have the MP3 library? Well, how do I get it? Well, there's money. You can get money involved, or you can work with an operating system that is already paying the owner of the MP3 that money. Similarly with how GIF is a owned proprietary format. The sound is the resource that we're managing mostly. Now, just another note, SDL Mixer does have both the difference between sound chunks, which are meant for like sound effects, and music, which are longer looping background tracks. Music has its own dedicated track and has some special features. Mixed chunks can work with a lot more variety of channels for mixing all your audio together. But I did wrap, as a resource manager, the chunk. I did not make a wrapper for the music stuff because as it turns out, the music is so simple to work with, there was really nothing else to add. And I'd imagine that with SDL3 coming out soon, that's probably even more likely to be the case. Anyway, if you want to work with a resource, you load the music with the file name of the resource that you're trying to load. This, I believe, also tries to work with the Let's go to that. So that is load music. Find, paste. There we are. There we are. Yes, this is trying to use my pack extractor, which doesn't work so well on Windows. So if you're working with this, you might want to just load music directly. That is a known bug that I am working on to try to get the pack loader to work from Windows. It seems that some files when they load up are a little bit more corrupt than I would like, and so I have to figure that out before I can really reliably use the pack extractor that I wanted to work with on Windows. But it works good in Linux. All right, moving on. Callbacks. So I didn't, well, note to self, I need to add some comments to this file. A callback is a general computing concept. JavaScript almost relies entirely on callbacks. Most UI programming relies on callbacks. Callbacks are a way to, in the future, call a function back to when we actually want something to happen. Generally speaking, they need to take some data, but the callback system generally doesn't need to know what that data is. It doesn't even know what the heck the function is that it's supposed to call. If you think back to my @exit discussion from a previous video, it works on the same concept. We are going to call the function that we provide at some future time. The exit, the one, however, takes no parameters. This callback system will take a parameter. And once again, here's another rabbit hole to go down. This is a function pointer. I'm going to have another video in the future where I talk about pointers in greater depth. But for now, a little bit of a hint. This is how you declare a variable that doesn't have data. It points to the memory location where a function should be, not where data should be. It is data. It is a pointer, because all pointers, whether they're pointers to data or a pointer to a function, is just a memory address. It is just the data or the number listing where in memory to find what we're looking for. In this case, we're hoping to find a function that returns void and takes a void pointer as its parameter. If this is valid to assign to any function that fits that prototype. And honestly, it doesn't even technically have to be a void pointer. It just needs to take a pointer as a data type. We also keep that data with us in the callback. We can even, this is just a quick allocator. So if we want to dynamically allocate them, we can do them. You can also just statically declare a variable as a callback. But generally speaking, with a lot of callbacks, we're going to be passing them around. So having a memory address for the callback will be handy to have. And then if you do create new, you must free. Whatever you create, you destroy. So on exit, at some point, you're going to have to clean up the callback. And then at that point, no longer use that memory address. And then we have the callback call function, which you just give it the callback. And what it's going to do is just make sure that this is not null. And then call this function, providing it this data. If that doesn't make any sense to you yet, wait till you see it in action. Moving on, alphabetically, because that's the order that this is sorted in. Let's talk about color. Color is not as simple as just having a red, a green, and a blue number value. If you've worked with computer digital pixel art ever, you probably are familiar with the idea that each pixel needs some level of red, some level of green, and some level of blue. And then sometimes you also have an alpha value or a transparency. So that is the most common way we deal with in computing a color. Some amount of red, some amount of green, and some amount of blue, and some amount of alpha, maybe. The fourth channel is optional. But that's not the only way we can deal with color. We can deal with 8-bit color in a 0 to 255 range. We can deal with the floating point where it's in 0 to 1. We can have hue, saturation, and lightness. There's also hue, saturation, value, but I went with the hue, saturation, lightness algorithm instead. Or we can have hex codes where this is red, this is green, and this is blue that you'd be working with if you did a lot of web design, web development. I created a color abstract class in order to make it easy to communicate between them. As I started working with different libraries like Vulkan and different file formats, it kind of became necessary to abstract it away, so I don't have to know what data source type it is. I just know I need to pass something as a color. I don't have to constantly convert between 0 to 255 or 0 to 1. It just made life simpler. Plus, being able to access colors as hue, saturation, and lightness lets us do some creative things with color and time. I can vary the lightness of a color and make something look like it's pulsing. I can vary the saturation on something and send something to grayscale, but still keep its shading and its colors and stuff. And in the hue, I can just vary things a little bit and keep things close to whatever the base color is. For instance, if I was working with fire, I want things to stay in the orange range. If I wanted some color variance and I was just adding some random values to each of the red, green, and blue categories, I'd end up not with a lot of fire colors. I end up with a lot of browns and sometimes some greens and blues, and it just doesn't work the way you would think. But working on it from hue, saturation, and lightness makes that a little bit better. And I made a whole bunch of global constant defines here to just if I want some prefabs. Color copying, this is done as a macro because generally all we're doing is just assigning two things. So this is a defined macro as opposed to this function here. This function will take a red, green, blue, and alpha value in the range of 0 to 1 and return a color with it. And this will actually, will assign that data to whatever I've set it to. Color compare. I want to create a color in the 8-bit range from 0 to 255, create it as a HSV, convert them from one format to another internally, just in case I need to make sure it's in one thing or another, which oftentimes when working with a graphics card, it needs to be one thing specifically. So it doesn't matter what the input type was, I guarantee that it's going to be something else. For SDL compatibility, SDL has its own color type. And this just makes sure that whatever my color has been represented at previously, it's going to go to SDL color. So just be aware when you're messing with color. Occasionally, if you don't have the color defined in the way you think it is, you'll end up either with something that's completely clear because I only gave it an alpha value of 0.5, when really I wanted an alpha value of 128. So it is not translucent, it's clear. That's pretty much all I'm going to talk about right now. There's a couple other utility functions here, and I did document this one, so we're good to go. Let's talk about config. No, I'm not going to talk about config just yet, but just so you know, this my JSON library is based on the ECMA standard specification of JSON, so it doesn't have anything more than the basic types of float and int and character and string and null as its basic types. But when we're dealing with games, we're oftentimes dealing with some more advanced data structures. And so instead of having to manually get all 4 values out of a JSON object, I wrote a function that handles that. And then if I'm saving a vector, I made one that will just save it as vector. And these basically pairs to each other. Whatever I write with this, I can read with this. And this will even work with a JSON formatted either as an array of 4 or a string containing the values with a space separation. Mostly I just work with the vector though. And same thing, I added one for color. But those are the basics. Moving on. Hash maps. So the reason why C gets such hate over the years is because its standard libraries don't do a lot for you. There's not a lot of good container classes. There's no good string class in C. There's no dynamic list. There's no internal hash map. Now, the people behind Gimp, yes, the GNU image manipulation, I can't speak today. GNU's image manipulation program, the open source alternative to Photoshop, they wrote their project in C and had the same frustrations that everyone else did. C doesn't have a lot of good container classes. So they made GLIB, a standard C library that adds in a whole bunch of standard container types, strings, lists, hash maps, all kinds of fun stuff. The problem with glib is that it has evolved to the point where it works fantastic on Unix-based systems, and it is an absolute nightmare setting up on Windows. It is also optimized beyond understanding, and one of the whole points behind my library here is that I'm not writing stuff that's most optimized. I'm writing stuff that is most easy to read. The goal of my code is not to replace glib. The goal of my code is to teach people how to work with these data structures, to see how they're implemented, so that one day they may go on to work in something like glib or make their own. Like back in remember Quake, we had the idlib. So this is my bare bones implementation of a hash map. I use the same algorithm, by the way, that they're using in glib. I did actually look into it and used some of its algorithm, and I cite it, so don't think like this is plagiarism. And it's open source, so it's allowed. But this is a hash map. This is a dumbed down implementation of it. We have a hash element, which is going to have a key and a value. This is the whole thing behind our hash value. That's not the same thing. The data, that's the data. Whole thing behind a hash map is if you've worked with a Python dictionary, a PHP associative array, a JavaScript object, you know what a hash map is, because that's basically how they're implemented. It's a key, like a string key to some value. Now, again, this is a dumbed down version of what we have in glib. So the glib hash, I can have anything, any data type, even arbitrary ones that I create, and it can use its internal algorithm to make a key out of it. And so when I want to access the hash map, I give it my key, and then I will get my data back. So whatever the key happens to be, we get the data. My version only works with text. In fact, specifically text line, which we'll get to at the end of this discussion, is a 128 character array. So it's not even, it is a limited number of letters and even can be in the key. But I find 128 characters is a reasonable key for most things. And then the data is arbitrary because I don't care what it is that you're keeping track of. That's up to you, the user of it. So this is where we kind of break C's strong typedness. The hash map itself has the list of keys. It's got a side, it's got a seed that's usually default. If you want to learn more about how hash maps work, this will make more sense. But again, this isn't a lecture on how hash maps work. This is just what we have available to us. If you want to make a new hash map, you just make a new, call new. When you're done with that, you free it up. Whatever you create, you destroy. This will allocate data. And by the way, since this is dynamically sized, it doesn't make sense to just have a hash map. You need to new a hash map. There's no just declaring something as hash map. You need to have a hash map pointer and then set your pointer equal to this new. And when you're done, you hand that pointer back to the free, and this will free the allocated hash map. Note this will not free the data in it. So I need to go through each of my elements before I call hash map free and clean up all of my data. Otherwise, these become dangling pointers, and we have what's called a memory leak. If I want to add something to my hash map, I give it a pointer to my hash map. It takes the key, takes a pointer to my key. So I give this a character right. Now this will be copied into this key. And only up to 127 characters get copied into it. And in the void pointer, I'm not copying the data. I'm just keeping this memory address saved in this memory address. That's how that works. Again, the hash map does not own the data. It will not clean up the data. If I want to get something out of my hash map, I give it a pointer to my hash map, and then I provide it my key. Now, if this were implemented in C++, I would be able to skip all of these passing the hash map to it, and it would all be member functions of the hash map class. C, when we're writing with a class structure in C, is just more typing. We need to always provide the this in C. It's not included when we have a class in C++. And again, just kind of pointing out that even though I'm writing this stuff in C, C++ is still important to know. All right, delete a value out of the hash map based on the key. This does not delete the data. This deletes the entry in the hash map. Now this returns get all values. This will give me an array of all the pointers to all the data. So if I do want to clean up at the end of its life a hash map and all of its data, I can get all the data as a list, and then I can just iterate through this list. More on that list, by the way, in two topics, and then just clean it up from there. I also have a little helper here if I want to give it a work function, which you'll see what that looks like also when I go into the list. This is a function pointer to be called for each member in the hash map, which again, I could even clean up all my data with that if I want. And if I want to output what is my hash map, this will print it out. So this was mostly used while I was writing it to make sure that it was working as designed. It works pretty well. I think I've squashed all the bugs I'm aware of in the hash map library. Let's talk about input before we go to the fun stuff. SDL is great for giving us different ways of accessing input events. There's an event structure, which you saw when I went through the game, where I had to pump the events, and that updates all of SDL's internal structures. And then I can start access things by either getting the state, or I can ask the SDL for the list of things that happened, the list of events, and then I can parse down into the events. Some things work really well by getting state. Some things work well by getting the other ones. I tried to make this input way to abstract it even a little bit further, because I don't know if you've ever played a video game before, but almost all of them allow you to remap the inputs. So rather than having to code everything where I'm asking for the A key, the D key, the W key, the S key, I want to ask for move left, move right, move back, move forward. And regardless of whatever the user has configured that to be, I just know that I can move forward and whatnot. So I'm not going to go into this too much. We even have access to joysticks and things. It is not 100% complete. There's still a couple features that I would like to add. I pretty much only add to this as I work on it with my own side projects. But it does work pretty well, and you'll see some examples of that in practice. There is a config file which we will load from when we initialize the system. So this configures all of the key mappings. And they can load inputs up specifically from this. And I can even just use the system to ask specifically for named commands or specific keys by name, so not by key code. So using something by name makes it easier to access if I pulled the key out of, say, a config file. The wheel is a bit more work to access. You can't use the regular get state, so you have to use the input system, and this will grab that. And all the different directions the wheel can move, and so on and so forth. You can even set callbacks, previous things. So I can say, given a named command, I can set a function to automatically call on press, on hold, on release, and whatever data I need to send with that. And then that'll be managed internally by the input system. And then again, some controller stuff I started working on. SDL does have a controller, like a game controller sub-library of the input stuff, but it doesn't really work well. I haven't had much success with it, so I've just decided to write my own. All right, now the list. Let me go to the beginning here. Here we define the work function we saw previously as a function that returns void and takes a pointer to void as its only parameter. So that's meant to work with the list, and it's meant to work with a hash map. So like if I wanted to declare a variable or a function as the function type, all I have to do is then call for each on it, and it will provide for each member. In this case, the void pointer is the data pointer. It will get the data. So for each element in the list, it will call whatever function I've defined it as for that. This is a so C++ has the vector class in its standard library. The C++ vector is an array that expands, and I believe internally it's been implemented as a linked list. Linked lists are a great little computer science topic of discussion, but in real world practice breaks down as a grossly inefficient way to store your data. For one thing, there's no way to force memory locality. So as I iterate through a linked list based list, I'll be jumping around in memory and accessing different pages, and it's actually slower than just iterating through a list where I have memory locality. So I tried to do the best of both worlds. I wrote this list class to be, it allocates an array, and each element in that array is now next to each other because it's a big array. And then it points to the data it needs to be. Now, this doesn't force the data to be in any way, shape, or form related to each other. That is still on the user to make sure that whatever is in this list is close in memory to its, but at least this makes it a little bit easier. I'm not forcing memory non-locality with this list. And as soon as I exceed the size of my pre-allocated list of elements, what happens is that it'll make a new list of elements, double in size, copy the pointers over to this, because all this is just a list of pointers, and then it increases the size and deletes the old list. So and it does not shrink. The idea is that it always starts off as a small list, and then it will grow. And if I'm going to keep a large list around, even though if I'm deleting things out of it, I probably will grow back up to that same size again. So the idea is that I'm not going to bother shrinking, and I double in size every time I expand, so that the more elements I have in the array, the less often I have to expand the array. Just like with the hash map, you're going to need to new this. It doesn't make sense to just declare a list as not a pointer. So you declare a list pointer, you set it equal to this new, and when you're done, you delete the list. Now again, this does not delete the data that this list is pointing to. You'll have to clean that up on your own. But I find this to be incredibly helpful, and I use these lists everywhere. Clears out the list, but does not free any data that the list may be pointing to. I did document this pretty well, but no data is freed. I even have some notes here. So go through the list. The most common things that you'll see in this list are list new, delete when we're done with it, and there is a get. There's a get for each swap indices. Well, this is not in any kind of useful order. Let's read the whole thing backwards and forwards till you have it memorized. All right, well, list append. This is how you add items to the end of the list. Or you can do prepend. You can add items to the beginning of the list. Or you can insert, giving it the number index you want to insert it into, and whatever happens to be there at that location and further, this gets pushed down the line. You can even set specifically what the nth is. That'll overwrite whatever happens to be at that memory address. Oh, here it is, get nth. This returns the data pointer that is at the nth location in list. If this number exceeds what's in list, it will return null. If list is bad, it will return null. It'll always return on null and error, or sometimes null is the answer though. So when you're building your own lists, make sure you understand what's in them to use this properly. And there's a get count as well somewhere. Get count. This is the other one that you're going to use most often. So you're going to, count equals get list count of a list. Then you're going to for loop I equals 0 while I is less than count I plus plus. And then inside that loop, you're going to get the nth that many times. And you're going to see that design pattern used throughout. Now, the matrix, I'm just kind of wave my hand at this because this is mostly going to be used when we deal with 3D stuff. Although if you'd like to model some rotations and things in with a matrix, even in 2D, you can feel free to go ahead and do that, although it's probably unnecessary. As I mentioned, the pack manager, I was trying to reproduce Quake's ability to compress all of its assets, which is great for both obscuring your data away from the user and having a smaller footprint on disk when you're finally releasing the game. Works great in Linux. I still have some bugs to work out on Windows, so avoid that if you're on Windows. If you're on Linux, have at it. Shapes. To the beginning of collision detection is going to be dealing with shapes, so I'm going to go into this in greater detail when I go through the collision testing stuff, but these are just some common ways of representing shapes in 2D. So this is 2D. So this is X and Y, circle X, Y, and radius, rectangle X, Y, width, and height. And then I have this generic shape type, which is a union of this with a type involved. So I know how to access it internally. Sometimes if I want to be able to compare between different things, I can just keep track of something as a shape. I don't have to necessarily keep track of whether it's a rect, a circle, or an edge, or if I add to this in the future, adding additional shapes. And all the different functions that would go with determining if they're overlapping. A couple other things that are in shape as well. I did provide Bezier curves, and so you can do kinds of stuff. This does not draw, though, because GFC is agnostic to the drawing type of our graphics type. Now text. This one's kind of handy. Like I said, C has no basic string type. We have plenty of things that say string. There is a string.h. There are string compare functions, but they are technically not strings the way we think of them in the modern sense. They are nothing more than character arrays, or more specifically, pointers to where we hope a character array exists. In fact, I even use the character array stuff. I still don't have a proper string type. GLIB does have its string type. I have not yet made my own string type, but I've found this to be very handy. Oftentimes in game development, most of the strings that we're dealing with are usually known fixed length strings. So for things like file names or player names or identifiers, they are generally known to either be a short thing, a line long, or maybe if I have like some dialogue, I would have like a block of text. So to make my life simpler, my text.h defines a word as 16 characters long, a line as 128 characters long, and a block as 1,024 characters long. If I need anything more robust than this, I'll have to, eventually make a string library. But because this doesn't expand, this is fast. It will just work with a character array. And I made all these accessors for string compare and memset for all the different things that I would need to do. And again, it's mostly just macros. So these are just using the standard C libraries to do the things. Just a fun note, snprintf, although as part of the C standard spec, Microsoft has made it a pain in the butt to ever use that properly. Although I do have some code somewhere where I deal with that issue, which probably is where I put it, in types.h. So just to start defining some common language, this type's header file was necessary. So C has no true Boolean value. Most modern languages don't have a true Boolean value, although some compilers will fake it. The reason being is that most modern chips do not handle anything smaller than what a word is. Now, not my text line word. A machine word is usually the register size for the chip. So if you're on a 64-bit machine, that should be 64 bits. Unless they've changed how that works since the last time I looked that up. But certainly when we were on 16-bit machines, it was 16 bits, and 32-bit machines, it was 32 bits. So the smallest data type I can allocate is whatever that happens to be. Now, again, like I said, compilers will kind of fake that. So if I'm declaring a bunch of integers, what it does is it'll basically pack them together if they're 16-bit. So it'll pack 4 of them if on a 64-bit machine, or 2 of them together if I'm on a 32-bit machine when I'm dealing with that. And same thing, characters, although they're 8 bits, it will, it'll just, how it organizes it in memory is up to the compiler at this point. But C has no true Boolean value. No, C++ has added one, which is why for ease of compatibility, I defined mine as capital bool. That's what this one is. I'm defining a short int, so this will be a signed 8-bit integer. So I can have negative bool. I only ever use it for 0 or 1. False and true are not always defined, so I do some compiler directives here. So the if not defined isn't just for include guards. It can be used to make sure some things are defined. So like if I haven't defined false, I will define false. If I haven't defined true, I will define true. We also have pi, because pi is going to be necessary for many, many, many things we do. In fact, pi is so useful, I made it specifically part for GFC, so I'll mostly just access it through GFC pi. And so each quarter of a circle, because pi is basically just the radians version of 180 degrees. So a complete circle is double pi. Half pi is 90 degrees, and pi and a half is going to be your 270 degrees, or your other right angle. So each of these are the cardinal 4 directions around a circle. And I've predefined them because, that's all that's necessary. And out to as many digits as I think is important. Epsilon is an extremely small number used to account for floating point number discrepancies, because there's a precision issue with floating point numbers because computers are limited and sometimes numbers are irrational. Epsilon is this extremely small number that we will use whenever we're comparing floating point values, and I want to make sure that things are within a certain threshold. More on that when we start dealing with collision detection. And because it's another magic number that we use a lot, the square root of 2 is there as well. Now, the math libraries all work in radians because, math works better that way. Humans work better in degrees because we can understand 360 better than 6.283185308. So generally speaking, I would say a good guideline is if you're writing something in a config file, work in degrees. But as soon as you put that into code, you want to live in radians. And these are just the simple multiplications that you need to convert between them. So if I want to go from radians to degrees, I take whatever my radian value is and just multiply it by 57.2, et cetera, et cetera. And if I want the opposite direction, if I have the degrees, this is the conversion to radians. So just multiply them out. Moving on. Shamelessly stolen from Quake 2 source code, like so many things in life. I modified it just a little bit to make it a little bit more human readable. Again, the goal of my code base is to be readable, not to be super efficient. So this will give me a random number, but I multiply the random number by 1,000 to just make sure that the random bits that I'm going to be basing this on are mathematically more random than not random. Not as good as Quake's, but it's still good enough. And then we can seed the random number generator, and we can also call the crandom. So random gives us a value between 0 and 1. GFC random gives us a value from -1 and +1, all in floating point. So if there's a min-max function that has not been defined, or macro that has not been defined, we will define it, and we define it with the ternary operator. So what this means is that this expression will evaluate to either A or B, based on whichever one is smaller, prioritizing A. And same thing, the max function will evaluate this as A or B, depending on which one is larger, prioritizing the first one, if they're the same thing, which shouldn't make a difference if they're the same thing. SDL rect stuff, although that should probably be my shapes at this point. It does need to be out here. Here is one that I'm going to go into in greater detail when we start working with it, probably later today if I have the time, in the video I plan on making. This is just basically bundles up, where's the allocate array. This code base I use everywhere whenever I'm allocating information, because C's philosophy is that it does not do more than what it is asked for. It allows the user to optimize it. It will not, when I call malloc, so when I want to memory allocate something, it will not check to see if it got 0. If you try to allocate 0 amount of memory, we will get a segmentation fault, because we cannot allocate 0 memory. So I do some sanity checking as well, and I slog the error, always log the error. I am philosophically against the concept of catch throw blocks, and we can debate this in the Discord if you'd like. I believe it is up to the programmer using your library to decide whether they want to catch your response or not, and forcing them to have to is a waste of code and time. What I much prefer, which I found when I worked in industry to be the preferred way for stability and error checking, is when something can go wrong, you log Y, and then you return some type so that the calling function doesn't need to crash. We can keep going. we also, do some more sanity checking, make sure that this actually provided us with some information we can use, and then mem setting the whole damn thing to 0. This is not done for you with malloc. There's a calloc which will allocate it for you, but also doesn't sanity check first. So I just made my own boilerplate code go away that I use anytime I'm trying to allocate something, and then check and then set it to 0. So I give it how much an element should be in this array, and then how many of them I want, and it just does that math real quick. So if I want a 1,000 sprites or 8,000 entities, this will return an array of zeroed out that many things. And because it's using standard malloc, I don't have to make a free function because we just use the standard C free function to clean it up. I'm going to undo because apparently I modified that file. All right. Last and certainly not least, the one that I'm going to have a separate video to go into just for math is the vector library. Now, this is not the same. Well, it kind of is the same, but it's not really the same as a C++ vector. C++ vector is a variable length array of things, which is kind of how a vector is considered in math. It is an array of things. It is more than one of something, where if I have only one numerical value to associate with something, it would be called a scalar. This is specifically to deal with vector math, trigonometry, all that fun stuff that we're going to be dealing with in order to have motion and action on the screen. So I explicitly define a couple vector types: 2D, 3D, and 4D. Why 4D? We'll get to that in 3D. We are mostly in this class going to be dealing with 2D vectors, and sometimes 3D vectors, but mostly 2D vectors. A macro to check to make sure to see if a vector value, so if the x and y is inside a rect, so as long as whatever I'm passing into the v and the r have an x, a y, and then the r has an r and an h, this macro can be used. Just like when I had the color, I have ways to just make vectors, so I don't have to constantly set everything to .x equals, .y equals. This just saves me some sanity. Although these do access the function stack, so use at your own caution. Convert a 3D vector to a 2D vector, dropping a 3D vector. This is sometimes handy. So if I want to access a 3D vector, it's just the x and y, or a 4D vector, it's just the x and y, or a 4D vector, it's just the x, y, and z. And then this up converts if you provide the z value. So sometimes it's handy to convert between vector sizes. More on that in 3D, or if you spent any time writing any shaders, you probably see that a lot, as a lot of things are represented as a 4D vector, but we usually use them as 3D vectors or even 2D vectors. So this is just trying to get feature parity with the vector libraries that you would see in any kind of 3D application. Set angle of a vector by its radians. This modifies the input. And in hindsight, I think I want to make an alternative version. It just returns a new vector. Everything should have both, in my opinion. Like sometimes you want to just modify something. Sometimes I want it saved as a separate vector. So I still need to add some love to this library. From angle, by the way, I believe, and I need to make a note of this in the code, but the 0 angle, the 0 radians is up. So up is 0, and then it rotates around the circle clockwise, if I remember this correctly. But I need to make sure I put that in the documentation. Otherwise, you can figure it out through experimentation. Figure out the angle, again, from the 0th line, what that angle is going to be with float. I think it's just a tan function inside. And all the fun stuff. Flip rotations, angle between degrees, angle between radians, clamp to make sure we're in plus or minus 2 pi or from 0 to 360, because when we're doing a lot of angle rotation math, sometimes we'll exceed 360 or go below 0. Sometimes we need array notation on things. So Quake did array notation for its vectors, so they were all just vectors of 0 and 1 and 2 and 3 to access the vectors, but I use the specifics by name Sometimes you need to convert back and forth if you ever want to interface with the library. Dot products. Oh, I'm going to go over dot products, don't you worry. And cross products. Those are going to be fun as well. I only have 3D cross products. I wonder if there's a... I need to look at a 2D cross products and what that would mean. Multiplying, copying, checking to see if they're equal, subtracting, adding. Oh, and like I said, this is a way to do the vector adding and an output in a separate thing. I just haven't done that for 2D yet. Vector scaling by a specific factor. What is this one? Source times factor. Oh, this is keeping the factor as a array. So the source x times factor x is where we're going to assign the dest x from. Meanwhile, it's a factor is a scalar, so the whole thing gets scaled by that value. Vector clear, vector 0, vector compare, vector negate, vector set, vector duplicate. If I'm dealing with pointers, this will make a new one. So this will generate data. This will generate data, and then vectors have to be freed after that. Reflect magnitude. So this is the Pythagorean theorem determining the vector length. This will check to see the magnitude between something, normalizing a vector. This determines the magnitude squared, so this avoids having to do a square root, because if you remember the Pythagorean theorem has a square root. This just lets us compare them, so it just keeps everything in squared for comparison, so we can avoid square roots. Set specific magnitude, all the stuff. All right, that is what I've provided for you in GFC. Most of it, as you saw, is documented. There's still some documentation to add and still some features to add. But when you are working on your projects this semester, keep in mind you have these tools to reach out for. All right, that'll be the end of this video, and I hope this proves to be helpful.